We now come to a much more difficult part of vectors, and that is multiplication of vectors. We're not going to need this until October, but I decided we might as well get it over with now. Now that we introduce vectors, you can add and subtract, you might as well learn about multiplication. It's sort of the job is done. It's like going to the dentist. It's a little painful, but it's good for you, and when it's behind you, the pain disappears. So I'm going to talk about multiplication of vectors, something that will not come back until October and later in the course. There are two ways that we multiply vectors, and one is called the dot product, often also called the scalar product. A dot B, a fat dot. And that's defined as it is a scalar, A of x times B of x, just a number, plus A of y times B of y, that's another number, plus A of z times B of z, that's another number. It is a scalar. Has no longer a direction. That is the dot product. So that's method number one. That's completely legitimate, and you can always use that. There is another way to find the dot product, depending upon what you're being given, how the problem is presented to you. If someone gives you the vector A, and you have the vector B, and you happen to know this angle between them, this angle theta, which has nothing to do with that angle theta, it's the angle between the two, then the dot product is also the following, and you may make an attempt to prove that. You project the vector B on A. This is that projection. The length of this vector is B cosine theta. And then the dot product is the magnitude of A times the magnitude of B times the cosine of the angle theta. The two are completely identical. Now you may ask me, you may say, gee, how do I know what theta is? How do I know I should take theta this angle, or maybe I should take theta this angle? I mean, what angle is A making with B? It makes no difference, because the cosine of this angle here is the same as the cosine of 360 degrees minus theta. So that makes no difference. Sometimes this is faster, depending upon how the problem is presented to you. Sometimes the other is faster. You can immediately see by looking at this, it's easier to see than looking here, that the dot product can be larger than 0, it can be equal to 0, and it can be smaller than 0. A and B are, by definition, always positive. They are the magnitude. But so it's determined by the cosine of theta. If the cosine of theta is larger than 0, well, then it's larger than 0. The cosine of theta can be 0. If the angle for theta is pi over 2, in other words, if the two vectors are perpendicular to each other, then the dot product is 0. And if this angle theta is between 90 degrees and 180 degrees, then the cosine is negative. We will see that at work, no pun implied, when we're going to deal with work in physics. You will see that we can do positive work and we can do negative work. And that has to do with this dot product. Work and energy are dot products. I could do an extremely simple example with you. The simplest that I can think of, perhaps it's almost an insult, it's not meant that way. Suppose we have A dot B, and A is the one that you already have on the blackboard there. Right here, that's A. But B is just 2y dot. 2y roof. That's all it is. Well, what is A dot B? A dot B, there's no x component of B. So that becomes 0. This term becomes 0. There is only a y component of B. So it is minus 5 times plus 2. So I get minus 10 because there is no z component. Simple as that. So it's minus 10. I can give you another example. Example 2. Suppose A itself is the unit vector in the y direction, and B is the unit vector in the z direction. Then A dot B is what? I want to hear it loud and clear. 0. Yeah, 0. It is 0. You don't even have to think about anything. You know that these two are at 90 degrees. If you want to waste your time and want to substitute it in here, you will see that it comes out to be 0. It should work, because clearly A of y means that this is 1. That's what it means. And B is z. That means that B of z, this is 1. And all the others do not exist. Well, I wish you luck with that. And we now go to a way more difficult part of multiplication. And that is vector multiplication, which is called the vector product. Or also called, most of the time I refer to it as the cross product. The cross product is written like so: A cross B equals C. It's a cross, very clear cross. And I will tell you how I remember, that is method number 1. I'm going to teach you, just like with the dot product, 2 methods. I will tell you method number 1, which is the one that always works. It's time consuming, but it always works. You write down here a matrix with 3 rows. The first row is x roof, y roof, z roof. The second one is A of x, A of y, A of z. It's important, if A is here first, that second row must be A. And the third row is then B. B of x, B of y, B of z. So these 6 are numbers, and these are the unit vectors. I repeat this here, verbatim. You'll see in a minute why I need that. And I will do the same here. Okay, and now comes the recipe. You go from the upper left-hand corner to the one in this direction. You multiply them all 3, and that's a plus sign. So you get AY, so C, which is the A cross B, equals AY times BZ times the X roof. But I'm not going to put the X roof in yet, because I have to subtract this one, minus sign, which has AZBY. So it is minus AZBY, and that is in the direction X. The next one is this one, AZBX. Minus this one, AXBZ. In the direction Y. And last but not least, AXBY minus AYBX. In the direction of the unit vector Z. So this part here is what we call C of x. It's the x component of this vector. And this we can call C of y, and this we can call C of z. So you can also write that vector then that C equals C of x, x roof, plus C of y, y roof, plus C of z, z roof. It's the cross product of A and B. We will have lots of exercises, lots of chances you will have on assignment 2 to play with this a little bit. Now comes my method number 2. And method number 2 is again, as we had with the dot product, is a geometrical method. Let me try to work on this board in between. If you know vector A, and you know vector B, and you know that the angle is theta, then the cross product, C, equals A cross B, is the magnitude of A times the magnitude of B times the sine of theta. Not the cosine of theta as we had before with the dot product. It is the sine of theta. So you can already immediately see that this will be 0 if theta is either 0 degrees or 180 degrees, whereas the dot product was 0 when the angle between them was 90 degrees. This number can be larger than 0. If the sine theta is larger than 0, it can also be smaller than 0. Now we only have the magnitude of the vector, and now comes the hardest part. What is the direction of the vector? And that is something that you have to engrave in your mind and not forget. The direction is found as follows. You take A, because it's first mentioned, and you rotate A over the shortest possible angle to B. If you had in your hand a corkscrew, and I will show that in a minute, then you turn the corkscrew as seen from your seats clockwise, and the corkscrew would go into the blackboard. And if the corkscrew goes into the blackboard, you will see the tail of the vector, and you will see a cross, little plus sign, and therefore we put that like so. A cross product is always perpendicular to both A and B. But it leaves you with two choices. It can either come out of the blackboard or it can go in the blackboard. And I just told you which convention to use. And I want to show that to you in a way that may appeal to ye more. This is what I have used before on my television help sessions that I've given at MIT. I have an apple, not an apple, this is a tomato. Not a tomato, it's a potato. I have a potato here, and here is a corkscrew. There's a corkscrew. I'm going to turn the corkscrew as seen from your side clockwise. And you'll see that the corkscrew goes into the potato in. That's the direction then of the vector. If we had B cross A, then you take B in your hands and you rotate it over the shortest angle to A. Now you have to rotate counterclockwise. And when you rotate counterclockwise, the corkscrew comes to you. There you go. And so the vector is now pointing in this direction. And if the vector is pointing towards you, then we would indicate that with a circle and a dot. In other words, for this vector, B cross A would have exactly the same magnitude, no difference, but it would be coming out of the blackboard. In other words, A cross B equals minus B cross A. Whereas A dot B is the same as B dot A. We will encounter cross products when we deal with torques and when we deal with angular momentum, which is not the easiest part of 801.